Hello again. Tonight we're going to talk about amateur observations and the reasons why professionals don't always use the data that amateurs record. So I was in a recent discussion with the Society of Amateur Radio Astronomers, or SARA. They have a monthly online session called Drake's Lounge. Yep, named after that Drake. So I brought up the topic of, because they wanted to discuss why their radio astronomy observations weren't being used by professional astronomy programs. And so I said, well, I've worked somewhat in that area, both with the SFAA and with the Minor Planet Center on how to get this stuff. And I think I've got some answers, but that wasn't the kind of the right venue for discussing it in detail. But I thought one of our evening sessions would be a better place to work the minutia, so to speak, without burdening their session. So that's what we're going to focus on tonight is, or jokingly, why for do you not like our stuff so much? My second language is English. My first language is humor. Yes, amateurs do record stuff. Yes, professionals do need data. Yes, professionals don't always like using amateur data, but why not? So that's what we'll get into. Is it's mostly about what you don't know about your equipment, what you don't pay attention to about the quality of your data, what you don't think you need to communicate. Why do I need that? I don't see any reason for that. The context of the observing session, and then how to package up the data for best, easiest consumption by professionals. And absent all of that, that's why amateur data is deemed not worthy. Now, one would think it should be a two-way street. Even the International Astronomical Union has recognized that there are far more amateurs out there capturing data far more often on a variety of targets than there are professionals. Professionals have big expensive observatories or spacecraft, and they can only look at so many different things. For example, if your observatory is below the equator, you're not seeing a lot of the things that the northern sky can see, and vice versa. If your probe happens to be the James Webb Space Telescope, it's not meaningful for it to go look back at the moon, the earth, or the sun, and over in that direction. So it can only see outward away from the sun. Otherwise, it could damage itself by accidentally going past the sun. But if that's the case, why wouldn't professionals want to use all that amateur data that seems to be available, has confirmed as being available, but that data could allow them to reach conclusions sooner, would allow them to build better models by having more data points. But what's the problem? It's not that amateurs aren't recording more data than professionals. Professionals actually have far larger data storage, not just terabytes, but petabytes of daily data, but it's targeted for specific things, specific frequencies, looking in specific directions kind of thing at certain times of the day. So it's not the volume of data that's the issue. It's that, if I take an amateur's data as a professional and it's not in the right format, then I've got to spend my resources, my grant money, my team to convert that data to something I can use in professional tools. Or the data is way out of range because it's not qualified, it's not calibrated, it's, as the saying goes, it's bad data, I can't use it. But sometimes it's good data, it's just the way in which it's stored, the way in which it's organized isn't compatible with the tools the professional uses on a regular basis. And so somebody's got to go write software that will map apples to oranges, so to speak. There is a myth, at least amongst some radio astronomers that are amateurs, that my backyard instrument is just not sensitive enough to pick up the same stuff that, 100+ meter giant ear telescope can pick up. And that's true. But then again, that big ear can only look at so many things. So even if it's something that needs to be brighter, easier to spot, the Minor Planet Center has found out that people with backyard telescopes are a noticeable portion of the observations finding new comets and asteroids, up until the latest gigapixel survey images, where they do deltas between two images over time. Also, I remember at one point in time, there was a brand new supernova that an amateur happened to spot first. And luckily he knew about how to file the data. So he filed the data and became one of, I think it was two people that spotted it that same evening. So, you don't have to have the massive expensive gear if the thing you're looking for is bright enough. You just happen to be looking in the right place at the right time and have the sufficient equipment to capture some information. But if you capture information and it's not good, or it's not formatted properly, professionals can't use it, and it consumes a lot of time to come to that conclusion. So what they'll typically say is it's not bad data, it's unqualified data. What is it that would render amateur data to be unqualified as identified by professional research projects? There's a lot of information that needs to be known about, as they say in optical telescopes, the optical train, all the parts from where the photons come in until you capture them. And if somebody just says, it's this brand of telescope, that's way insufficient information. Don't know anything about it. But if you said, oh, it's a 10-inch, okay, that's a little better. There's a whole lot of delta, a lot of minutia that you may not think is valuable, but when you're doing scientific research, it's very valuable. Well, you'll hear an amateur say, well, what else do you guys want? Well, I want a lot more information about your equipment. I need to know, like, who said it's good for doing those kinds of things? Did you test your equipment against a specific set of values? You put some fake star up there, measure it at a certain brightness. Is that the brightness you actually measured? Or in the case of radio astronomy, pointed at certain bright radio stellar objects that have known energy levels, and is that the energy level you got? So it's not just the information about the instrument, it's what's it, has been verified to be good at what level, and then how about the calibration of it? Now that you've got some data, if the professional's looking for it in a certain way and the amateur's producing it in another way, somebody's got to go out there, convert the apples to oranges, and the professionals don't want to consume their grant resources, their team doing that kind of stuff. So please put it in their format, conformance to expected norms. It's not just a file with data in it. It's entire folders and structures and sets of files in certain formats that the professionals' tools will be expecting as observational data before they'd be willing to process it. If you give them the data and nothing is confirmed that it's in that structure, that format, first thing they need is tools that will do that analysis for them. Otherwise, they're going to be wasting their resources only to find out that, well, your data is like 80% there, it's 20% not conforming to what's expected. So, yeah, that's a problem. So what would they need to know about my instruments? Not just manufacturers and models, but hardware and software versions, because it may be the same brand and model, but they might have different production runs, different changes over time. So, if you have the hardware software versions, that's great. If you have the serial number, that can help to identify a batch run, particular version of that stuff. And then you need that for all the components in the train that captured the data. In the case of radio astronomy, that's the primary antenna, the secondary, amplifiers, filters, any up-down converters, tuners, whether they're crystal or phase-locked loop, receivers, how good are they? All that stuff has to be packaged up with the observation data before a professional will know, okay, I understand what your data is, where it's coming from, that kind of stuff. And then even if it's the same product, there could be different versions of it and different production runs. So I remember Meade being notorious for this. If you bought a particular model of Meade telescope, you had to always look on the inside to see if the parts were what the schematic said they were, or if it was just like, well, we don't have any capacitors that are 15,000 microfarad, so we threw in some 12,000 microfarad. If you did that with a camera, or if you did that with a pen diode amplifier, you're not going to get the same data out the back end. So it's understanding all that minutia that the average amateur doesn't either recognize or care about, that the professional community will say, if I haven't got that, I don't know what I've got. And then the actual installation of it. In the case of electronics, it's things like, oh, did you remember to ground your electronics? There could be background noise in your data that would not be there if you had properly grounded your equipment. What's your power source? If you've got a ratty power supply that has lots of ripple in it, your data may not be as flat as you expect it to be. Different sites, you put the same equipment at two different sites, and one site has a little bit of tree over on that side. So as the telescope moves over to there, the signal gets a little wonky based upon there's some shrubbery over there. Different values from different hardware, even of the same parts. The parts can have batch runs. And as I mentioned, part swaps by manufacturers. Now, instrument certification is basically a way of somebody writing up something that puts it on the line that I claim this piece of equipment to be good for the following observations. Limits, upper limits, lower limits, norms, curves that show responses to things. That's certification of the equipment. Now, obviously, you can go back and look at that stuff if you know the manufacturer and the model and the versions. You need the actual data itself, the certification data, in the package that you present to the professional. So we're getting way beyond what the average amateur would be willing to record with every session. Now that it's been certified, what about calibration? Sometimes equipment has components that are adjustable, and therefore they can throw off the observations. You need to know what the calibration data is. When was the last time it was calibrated? Does it need to be calibrated or not? Is it self-calibrating? Which is not often, but sometimes. What was the process by which it was calibrated? Who signed off on the calibration? Calibration is not like just a thermometer at a certain temperature number. Calibration is about a set of values over a range and the probability of getting the same value out the same, on recurring observations. That's part of the calibration process, because once data has been properly certified and calibrated, if it seems to be a little off, professional software can go in there and rebias the data to, observations from one site equal observations from another site. If the data hasn't been calibrated and the calibration data is not up to par, then professionals would probably not want to waste their time and their grant resources and maybe their professional basis by using data that's unqualified. As somebody who works with medical devices, this one's always a stickler for me, is units of measure. I just read a value. It's 12. 12 what? Well, 12. It's an electrical value. Oh, good. Was that electrical value volts, electron volts, amperes, watts, coulombs? What was the unit of measure? Okay, you have to know more about your instrument to know that the value that you're reading has a certain basis in international standards-based units of measure, and you should be communicating your observations in that. Sometimes there's actually structure to the individual data samples that the professional community will expect, like coordinates. Are those celestial coordinates, galactic coordinates? How did you record right ascension? Did you record it as hours, minutes, seconds, or degrees, minutes, seconds? Did you record it as sesagesimal, hours, minutes, seconds, or is it fractional hours, fractional degrees? Different professional astronomy groups will expect the data in certain formats. Let's say you have some really big numbers or really small numbers like electron volts or, power units. Those can be, times 10 to the minus whatever. If your units of measure are nanometers or microns or angstroms, then that times 10 to the whatever is going to be different based upon who's recording the data. But if it's all in raw units, be it electron volts or meters. Now everybody's scientific notation has the same scaling. So you want to scale it such that it's measured in the rawest base value as opposed to some scaled value that makes it easier for people to read. I don't want to see that it's a single digit followed by 5 decimal digits. I want to know that it's 37. Well, now if you want it to be 37, you're going to have to say, is that microns? Is it nanometers? Because you don't have any scale in it. And then labeling things correctly. I call my stuff date, but you see the professional is looking for it to be called timestamp. They're kind of the same thing. Can't you just use my data? Nope, because the software is looking for timestamp, not for date. And then once you have like a multi-hour session of observing, you're not going to be gathering data for the entire session. You're going to be doing an observation for a while, stopping, tweaking some things, and then doing more observations. So your data is going to come in batches for that session. How is the data batched? Is it simply a zip file? Or is it a file folder of subfolders with timestamps for folder names and that kind of stuff? And how do you batch it all together to make an observing session? There's standards that the professionals expect that to conform to. Then about, if I'm a retired individual and I've got plenty of time and the skies are clear and I want to make observing sessions 6 nights out of 7 for the next week and I have the time and my equipment's working, great. What happened during your observing session? Well, the weather is going to be changing. What was the weather like when you were observing? If you did this over a season and you didn't trim things back, was there any foliage that was getting in your way? If you haven't got weather sensors or cameras to capture this stuff, the U.S. Weather Service can provide you with weather reports that you can draw from, or if you've got the right software, download. I know that when I was writing software to do radio astronomy, there was actually a web link you could go to and give it basically your airport code, and it would give you all the weather parameters as data, not as pictures or a website, but as data that you could process. And there was a standard for how the data is reported. And then here's the strange one. Whenever there's an observation in professional use, there's always a notes section for the observation session. Now, what might that be? We had a little dew on the instruments. Well, that might change things. Or there was a lot of mosquitoes around. Well, that might change things. So it's just a notes section. So if all your data passes muster from every other perspective, is there anything else you'd like to report? Well, that needs to be included in the package of your observation, assuming it's not something catastrophic like my instrument died halfway through the session. Now, all of this gets to be the more complicated aspect of how do you package up all this session data? And it's far more than one file in, FITS format. So you have to capture all the aspects of your observing session and put it in all the right structures and formats in order for the professional data processing systems to easily uptake that data and include it in their results. But when you get onto the minutiae, it's a lot of stuff. And if you're doing this as an individual, you may not have the resources and the software talents to package up all this stuff. So it'd be really nice if somebody would lay the groundwork before you. But if you submit it as is, and it's close but no cigar, as the saying goes, and then somebody points out what you're missing, well, what do they need that for? Well, that would be an unacceptable excuse, and your data would be instantly unqualified because you don't have an appreciation of the data that you're giving to others that you expect them to use. Here's a simple item. Time of day. If I'm using my local time zone and I don't tell you what the time zone is, that's unacceptable data. It's expected to be universal time aligned, so UTC, and it's not expected to include an AM, PM. It's expected to be military time, 24-hour basis. And where you took it from, so you need the coordinates. Because if you've ever studied the geopolitical time zones, you'll realize that be elongated across longitudes. And if that's the case, and you said, well, it's a +6 hours offset UTC because I'm in a central time zone. And you look at some of the central time zone, and some of it's way up over here, some of it's way down there. And the actual difference in observing time can be more than an hour. So that's why you can't use time zone, because time zones are political, and longitude off of UTC is a better way of describing how far off your time might be from a sun angle perspective. What about the time accuracy itself? I looked at my watch. It was close enough, plus or minus a minute. Like the speed of light is a very fast animal, and lots of things can change in a very short period of time. And since we're observing photons, they're moving at the speed of light. So, yeah. And if you're taking, if as a professional, you're taking observations from several observing sites around the globe, having the date and time not be precise means you can't align things. Because if I look at something that's directly overhead from Florida, it's not going to be directly overhead in California or Europe. So in order to take the same time of day and get the same observation so I can pair them up for improving the analysis, I need to know exactly what time it was there, and there. As accurate as you can get. Now, it's understood that amateurs aren't going to afford a $100,000 hydrogen maser oscillator, or even a probably $400 to $600 rubidium GPS corrected time source or oscillator. But you can get a GPS receiver, and you can have it with a thing called a pulse per second interface. So it can receive a tick that is accurate from the satellite at 10 nanoseconds. Now, given drift, it may not be precisely 10 nanoseconds. It may be 20 microseconds. But 20 microseconds is far better than, a half a minute. You want it to be UTC based. You want it to be 24-hour. You want it to be the highest network time protocol, or NTP, aligned accuracy you can. And that's just for time of day. Date. The GPS can give you the location, but don't use GPS altitude. Use a barometer for that. Far more accurate, because as the satellites are going overhead, they actually bob up and down in the atmosphere. So if you wanted to look at it from sampling data to packaging it up for a session, these are all the things you have to pay attention to. And this is just kind of like the tip of the iceberg, so to speak. So it's understandable that amateurs aren't aware of this stuff, don't have a feeling for the serious nature of this stuff, and could really use something that would tell them what to do, how to package up their data so it would be acceptable. Let's just take one sample of a specific frequency of amplitude. What's the range of it? What's the scaling of it? What's the units of measure? Now I need to know all that stuff. When was it captured? What's the timestamp? What's the timestamp accuracy? When I store it, how many bits of data does it take up? Because if I'm packing these things together, I want to know how many samples I have. What's the sample rate? How many samples per second does it take? If I'm storing this thing as scientific notation, the number of digits of precision varies. Is it 32-bit storage, 64-bit storage? And if I have a piece of electronics capturing the data, what's the certification and calibration record associated with the equipment taking those samples? When did I start capturing? For how long was I capturing? The clock rate of the samples per second. What's my oscillator's clock accuracy? How do I pack all that together? What's the packing format? How did I store all my samples such that they can be referenced? It's not just going to be a FITS file. It's actually database of data. And now, since it's a database, you need to talk about the schema, the tables, and then the headers and the columns and the rows within the data. What are in the folders? Because there's not just one file folder in a sampling session. There might be 30 different folders there that have all kinds of data in there beyond just the actual sample data. And then when you want to send that to someone, obviously sending them the uncompressed data might be 100 megabytes, but it's very low density data, so it packs well. What's the compression format? How should I compress these things? Is it a tarball? Is it just zip? Is it 7-zip? You need to know that kind of stuff. And then when I package up all my observations, did I give you multiple sessions of observations, or did I separate that out into separate sets of data? I need to know that stuff if I'm a professional. So here's an example. Let's just stick with the radio astronomy. The US has an organization called the NRAO. They're a unit of the National Science Foundation, and they have a software group that developed a set of software programs used by professionals called CASA, and they have a prescribed format called a measurement set. That's the collective set, all the different folders and such. And then each of those files has its own data set format. So there's documentation on this. But first you have to have an appreciation for all the deep rabbit hole minutia of all that data. But I think it would be better if the folks that do CASA could actually join us in the middle, so to speak. So they could come out and say, well, yeah, it needs to be CASA format. Go read the 200 pages worth of documentation and go learn the technology needed to understand it and have empathy for it. Like that's not going to fly. But until the data is exactly as not the professionals, but the software the professionals use is conformant, close enough's not going to be good enough. And if they were to use your data and then later find out it was unqualified, if there's no software to verify the qualification of the data, then they risk their position in the professional community for using unqualified data and come away with maybe not peer-reviewed or not verifiable results. So they've got a lot on the line as professionals. But you know what? The professionals have help. If you look at a big observatory, they have equipment technicians. They have what is known as data wranglers. These are the people that take the raw data from the instruments and do put it in the format that the professionals expect, so that Monday morning when you come in, you have an email in your inbox that says, here's all your data nicely packaged as direct importable by the CASA software. So they have professionals that help them. And when they do need to make changes, they have access to professional software developers that will not only develop things like the CASA software, but also maintain it. If they find bugs in it, correct the bugs, improve the capabilities of it. You want to add new data sources, they have to know how to qualify the data sources. So, if for example, I'm working with the VLA not only has their own data wranglers, they have their own data backend processors. So they've got their own supercomputers that not only analyze the data for the VLA, they'll also analyze data from ALMA. They'll also analyze data from Keck. Not actually Keck, but the radio telescope on the same mountain as Keck. They'll not only do the analysis, they'll give you the back-end results. So all you got to do is look at, in conclusion, there it is. But amateurs don't have that kinds of stuff. I've actually attempted to set up what is known as a CASA node. This is a computer that can run the CASA software, and it runs like molasses because I just had a quad-core Raspberry Pi 4 to devote to it full time. And when you're comparing it against the supercomputer, that's going to take you months for something they can do in hours. So yeah, I need not only them to make it easy for me to give them my data in a qualified manner, I would be appreciative if they would process my data, because they're supercomputers aren't always fully occupied. They may have a couple of hundred GPUs that they can donate to analyzing your amateur data for you if it was in the right format. Now you might say, oh, there's lots of professional software out there. There's lots of open source software out there that amateurs use all the time. There's all kinds of device interfaces and libraries that will gather data, but it's in a format that only that application knows. Or a handful of amateurs will share the data in a proprietary format, or a format that only that vendor knows how to produce it, and only that vendor's analysis software knows how to open it up and process it. That's not going to fly with the professional community. It's got to be something that's conformant to professional formats and professional standards. Just documenting your proprietary format's not sufficient. Just saying, well, if you pack it into a FITS file, that's not sufficient. If you say, well, if you take my proprietary file and then you run this Python library that I'm going to give you the source code for, you can pick out the observation values. That's not going to fly because somebody still has to write the software to take it from your proprietary format and put it into the format that the professionals need. So the best way to describe this is if you looked into CASA, you'd find that whenever there is a unique path of data that needs to be processed, CASA supports something called a pipeline. This is all the little steps in the software, different software tools that will take the data in, mold it, shape it, check for errors, check for out of bounds conditions, will pre-process the data. And they know how to do that because they know those instruments based upon the data coming in on the pipeline. So they can have a pipeline for VLA, a pipeline for ALMA. So what it comes down to is, gee, if you just had enough funding, if the NRAO would give you some funding, create a pipeline for amateurs. Now, this is obviously just for radio astronomy, but if you could create a pipeline for amateur radio astronomy, it would create something that would verify, qualify, expect a particular file, and if it doesn't have it, error you out. Expect file values to be in a certain place in a certain range. Expect time and date to be within a certain accuracy in a certain format. And if that pipeline said, nope, not good enough, then it wouldn't busy up the professionals to qualify the data. And when it came out the back end of the grooming pipeline, now the professionals probably wouldn't mind using it. But until we have that amateur pipeline in place, it's going to be unqualified data. And until it gets qualified, professionals are not going to be wanting to use it. But, this is a lot more effort, a lot higher, loftier goal than just, well, I'm going to put my pixels into a FITS file. So in summary, it is indeed true that amateurs make far more observations, far more often, and at far more targets than professionals do. Data that's suitable for amateurs is unlikely to be qualified for professional use. You need to know your instruments and communicate your instruments in detail in observation. You need to certify your instruments that they're good for doing what you're using them for. Doesn't want to be off-label, as the medical community would say. You need to know that your instruments are calibrated. You need to record the data using the proper units of measure and scaling and such. You need to package up your data, files, folders, formats in a manner that's conformant to what the professionals expect. And the amateur community can start a dialogue with professional observing efforts to maybe get a pipeline for CASA for amateurs. And, as the minor planet studies community has found out, amateurs can bring data to the table that's usable so long as it's qualified data. And there's a lot more amateurs than there are professionals, as the saying goes. Enough said. And then links as usual, if you want to know what those formats are. And if you know what the libraries are and how you get weather reports and how do you get your time of day accurate, all that information. And like I said, this was capturing all the information that the serious amateurs are going to need, and then I'll put it out after I edit it on the public YouTube channel. And then I can tell folks at Sarah, hey, go look at this video, see if it's something you're interested in. Comments, questions?
Looks like a lot of work.
Well, that's
exactly. Yeah.
The amateur that goes out and takes what they believe to be a really good picture of the Orion Nebula. If you then look at a professional's picture of the same thing, you're oblivious to the level of detail needed to get what looks to be exactly the same picture. And in radio astronomy, it's the same thing. If you said, hey, I think I've measured a particular radio signal source that's a quasar. good? Well, if you're a beginning radio amateur, you know it's not a picture. It's just like data. It's a waveform. And even the professionals that only have a single point source, for them, it's data. It's a waveform. What's the level of noise in your equipment versus the level of noise in their helium-cooled equipment? You know, you've got apples and oranges there. So you've got to find some way of fully describing the data. And I think the professionals do that. The amateurs need to start fully describing their data in a manner that you can compare apples to apples. Now, the noise levels may be different, but if the signal's high enough, if your signal to noise ratio is high enough, maybe you can clip off the noise from the bottom and you can now have apples and apples. So it's meaningful to have the discussion. I think it would actually empower amateurs if they had something that would guide them in the process and software that would say good enough or not good enough and why not good enough. I liken it to when you first start learning how to program a computer and you're confronted with this thing called an assembler or a compiler. You need to write your code the way the assembler or compiler expects it. If not, you get syntax error or your program blows up. Well, if you're getting syntax error, that means the data you're creating, the program you're creating, does not match the expectations of the software professionally used to assemble the machine code or to compile the higher level language code. Even if it's something as simple as Python, JavaScript, Java, they all have a piece of software that sits between you and the computer that will look at whatever you've produced and then see, is it good enough? And I think that if amateurs had some automation in CASA, that radio astronomers that are amateurs could have a means whereby their data could become qualified. And much like a new programmer learning to write code, once you realize the assembler or the compiler is an impenetrable wall, if you give it a higher level language program and it says syntax error, you probably won't be able to run your program until you correct that syntax error. If it's a warning, that's different. But if it's an error, it probably won't produce the machine code to make your program run, or it might not. Your Python software might blow up. Not explosive, but not continue the program. It may terminate the program abnormally, and therefore you got to go fix it. Same thing would be true in this case. If there was an amateur pipeline in CASA and you dumped in what you thought was the best data possible, and it came back and said, not so fast. What about this? Do you really need that? Wrong answer. Go back and fix it. Go back and provide the data. And then you can take it to the next step. So it's what they refer to as stepwise refinement. Until you get all of those issues resolved, until you give it all the data of the right quality, your observation data is not going to be suitable for professional use. Now, on the other hand, if you do have a pipeline for amateurs and it passes that pipeline, maybe the VLA might have some spare cycles to run your data through and will produce the pretty picture from the radio image. So there should be a method to your madness to work up from raw amateur data to professional grade data, because your data can look pretty good too. In my living room, I have a wall hanging that I won at an astronomers group meeting up in Orlando as kind of a raffle item that they offered me. I think it was $25, or I can get a free framed picture of, I think it's 5 pictures from the VLA in color. They're obviously false color, but lovely color pictures. So I said, I want those because I want professional grade, fully processed radio astronomy images that I can point to and go, if I'm going to strive for something, that's what I'm going to strive for. So if there were a CASA pipeline for amateurs and I had data that I was proud of, I would keep bouncing off of that check service of the amateur pipeline until it said, looks good enough. And then if I submit it into my Raspberry Pi running a CASA site. If it took a month or 2 months to process the data and the end result is I get a lovely, pretty picture. That's just an extended version of, when somebody goes by an optical telescope and they put a whatever they can afford camera on the back end and they take that first picture before they start concerning themselves with like darks and flats and noise and cleanliness of optics and all that minutia. They look at it and go, hey, that's a nice picture. And other people that don't understand the level of detail may go, that's a nice picture, because they don't have an appreciation for how much better it could be with the same amateur equipment taken by the same amateur if you just touch things up a bit. So that's the whole idea, is if we can get the amateurs to touch things up far more than a little bit, a lot, professional community might be willing to start using your data. More things might be found out, more conclusions might be arrived at sooner because there's more data. Okay, I'll stand down for my soapbox now.
Yeah.
So I see that it looks like Jay's on. I don't know if he's been paying attention because it's dark out there. I think he's outside.
Is that a live camera?
Jay's got some experience of.
I'm here.
Jay's got some experience of all the minutiae you have to go through to improve the quality of what you're doing. There's a lot of it. And that's way before you get to, helium cooled instruments. Okay. Any other comments or questions?
Nope.
Then I'll stop recording.